Hello, welcome to this presentation. My name is Suelen Laurindo. I'm a PhD student at the Federal University of Santa Catarina in Brazil. I'll present a paper entitled Assessment of Different Algorithms to Solve the Set Cover Problem in a Relay Selection Technique. My presentation is divided into 5 topics. Firstly, I'll talk about the motivation that led us to work with relay selection in a wireless sense network. Then, I'll present the proposed optimized relay selection technique, ORST technique. In the sequence, I'll present the algorithms used to solve the ORST set cover problem. Then, I'll present the experimental scenarios, followed by the experimental results, and finally some conclusions and future work will be pointed out. Wireless sense networks are one of the enabling technologies for the real concept implementations such as those commonly found in the Industry 4.0 and in IoT. In this way, these networks can be used as a solution for many applications, contributing to improve daily lives in several areas, for example, healthcare, smart cities, or smart agriculture. However, wireless sense networks are subject to restrictions on the reliability of their communications. In this kind of network, many messages can be lost due to electromagnetic noise or because there are other devices operating in the same frequency band. Consequently, this problem may lead to a severe reduction of the achievable throughput. So, to improve the reliability of wireless sense network, cooperative diversity can be used. Cooperative diversity considers the existence of nodes that will cooperate with the transmit-receive pair and increase the chances of sent messages being received in the receiver node. For example, consider this network with the coordinator in the center and 15 nodes around it. The nodes 6, 7, 9, 11, and 13 are outside of the coordinator area, but this network considers cooperative diversity, and the nodes 1, 2, 3, and 4 are the relay nodes. These nodes can communicate directly with the coordinator and also listen to the nodes that are outside of the coordinator area. In this case, all nodes in these networks can communicate with the coordinator node. But a problem may arise when more relay than the necessary are selected, because this will increase the number of repeated messages and the energy consumption. In this way, the performance of the cooperative retransmission techniques depends heavily on the efficiency of the relay selection technique. To perform the adequate relay selection, in a recent work, we proposed a relay selection technique named Optimized Relay Selection Technique, ORST technique. The ORST technique seeks to select the smallest number of relay nodes and at the same time ensure that all nodes will communicate with the coordinator node. The ORST technique can be characterized as a research allocation algorithm that may be reduced to the classic set covering problem applied to wireless sense network. The set covering problem seeks to find the minimum number of sets that contain all elements of all datasets. The ORST technique considers the relay node as an optimization problem and perform the relay selection using this object function, considering the available energy of each node, and the beta variable is a constant used so that the nodes with the largest amount of energy has the lowest cost in the object function. Each node will calculate its object function value and send this information to the coordinator node. The coordinator will receive the object function value of each node and solve this optimization problem. I won't go into mathematical details so as not to prolong the presentation time, but we can consider with these restrictions, the coordinator will select the smallest number of relay nodes and ensure at the same time that every node has a retrievable relay. In other words, the wireless sense network problem treated in this paper consists of finding the smallest number of elements that cover the entire network. The set cover problem can be solved by more than one technique. However, when dealing with a problem in the wireless sense network, characteristics such as real-time and reliability need to be considered. It is important to use adequate relay selection algorithms that allow getting better solution in a short time and without compromising the network performance. In this way, this paper assesses the performance and quality of different set cover problems algorithms to solve the optimization problem of the ORST technique. In addition, we consider an analysis of the computational time required to solve the set cover problem generated in the relay selection, and an analysis of the operation of the networks when using each of these algorithms. So, to solve the ORST set cover problem, we select 3 state-of-the-art algorithms, which are braiding bound, greedy, and genetic. The first one, it is the braiding bound. It uses a divide and conquer technique. The goal of this algorithm is divide the feasible solution into subdivisions and use a tree search strategy to implicitly enumerate each of the possible solutions of a given problem, applying pruning rules to eliminating branches that cannot lead to a better solution, or generating a new subproblem until find the best solution. The second one is the greedy algorithm. It makes a sequence of decisions, and in each decision make the choice that look the best at the moment. Even true, greedy choice doesn't always lead to the global optimal decision. And after the choice is made, it isn't possible to go back and choose another option. In this figure, the object is to select the elements that result in the largest sum. It is possible to observe that the algorithm selected the largest number in each iteration, but didn't result in the best possible solution, which is the one in the right. The last one is the genetic algorithm. It was inspired by the theory of natural evolution, where only individuals who evolve survive, as you can see in this GIF. It considers characteristics as a survival of fittest, reproduction, and mutation of a population to gather better solutions to a problem. As you can see in this flowchart, the algorithms initially generate a set of individuals who is named population. Each individual is qualified according a fitness value, and the exit criterion can be the maximum number of repetition. This number depends on the problem. If the criteria has not been reached, the algorithm flows for the basic operation, which are selection, crossover, and mutation. In the selection, 2 individuals are selected in the population. In the crossover, a new individual is generated based on the 2 individuals selected. And in the mutation, an individual undergoes a change in his genes. and this process occurs until the best solution is found. To evaluate the performance of the algorithms, we performed a simulation assessment using the network simulations tool Omnet++ and the wireless sense network framework Castalia, which allow to represent a real scenario. The simulation execution time was set to 450 seconds, and in this table we can see some parameters that were used. We consider 5 scenarios with 21, 41, 61, 81, and 101 nodes, where one of the nodes are configured as a coordinator node. The simulation area was 50 by 50 meters. The radio used as CC2420, and the MAC layer was IEEE 802.15.4. All the algorithms have been coded in C++ language and were tested on the same computer. The simulation assessment was performed considering the execution time of each algorithm to perform the relay selection. In our model, the coordinator node must use only 15.36 milliseconds to perform the relay selection and sending the beacon message. In addition, other metrics were used to evaluate the network quality performance, namely success rate, number of cooperations per node, energy consumption, and the percentage of duplicated messages. This figure illustrates the correlation between the success rate in the bar chart and the time used by perform the relay selection in the line chart. It is possible to observe that in the genetic algorithm, in the dark green line, needs a longer time than the grid algorithms in the light green line, and present a similar success rate. So, it is evident that the genetic algorithm is an unfeasible solution, exceeding the time allowed to the coordinator to perform the relay selection, and presents a similar success rate. And the breaking bound algorithm solves the optimization problem within a time allowed for the coordinator and presents the best success rate. In this figure, we can see the usual retransmissions message. It is possible to observe that when the network presents a lot of usual retransmissions messages, some unnecessary relay has been selected and consequently duplicated messages are being delivered. So we can see that the breaking bound algorithms in the red line present the best results. You can see in the scenario with 100 nodes, the percentage of usual message was near to 0. And between the genetic and the grid algorithms, both have selected unnecessary relay nodes, and which resulted in the usual retransmissions messages. This figure illustrates the correlation between the average number of cooperations exchanged per node in the bar chart and the energy consumption in the line chart. It is possible to observe that both the energy consumptions and the average number of cooperations exchanged were very similar for all the algorithms. This behavior is a consequence of the smallest number of selected relay due to optimization problem used to model all the algorithms used. As a conclusion, the grid algorithm can be considered a viable solution, considering characteristics such as the simplicity of implementation and the extremely low execution time. Besides, that the success rate were very similar to the breaking bound algorithm, and the breaking bound algorithm was the approach that presented the best results in all metrics and can be considered the best solution. And as a future work, it is intended to merge cooperative diverse technique with a network coding technique. Besides, we are implementing the proposed technique in a real wireless network prototype. Thank you for listening to me.